this video, we'll cover the last part of section 6.3, which is talking about something called logistic models. Okay, just a reminder of what we've talked about. Remember this phrase that if the rate of change of y, so rate of change means a derivative, so dy, most of the time dt, is proportional to y. So remember, we have this k value, which is the constant of proportionality. So if you have your rate of change is proportional to the actual value that you're looking at, then y follows an exponential model. So if you're ever giving something like this, then we know that if you solve for y, which we did on a past video, you're going to have an exponential growth model. So the general solution of this, you get y equals c times e to the kt. All right, but what happens is a lot of times with an exponential model, we talk about like population growth and things like that, but this model is actually only valid under ideal conditions and unlimited resources. So that is, if I have a population, let's say, of 2 rabbits, and they start to breed and make multiple rabbits, then at first it looks like it's going to be an exponential growth model, but in reality, the population of rabbits does not approach infinity because we don't have ideal conditions. We're not immortal beings, and we don't have unlimited resources. So in reality, a population often increases exponentially in its early stages, but eventually levels off and approaches its carrying capacity. All right, so given a, let's say these 2 rabbits, again, and let's say they're on an island, and so these 2 rabbits start to multiply, but this island only has so much food and so much space for these rabbits to inhabit. So they have to reach a certain carrying capacity that that island can hold, given the resources. So this is the maximum population that the environment is capable of sustaining. So what we have is, instead of this exponential model that we've been looking at, because that doesn't properly show what a real population growth would look like, we have a logistics model, which incorporates the fact that the relative growth rate decreases as the population increases and becomes negative if P ever exceeds its carrying capacity. So that is, if I put 10 rabbits in a really, really small cage and don't feed them enough, then you can imagine what would start to happen. So the simplest expression for this relative growth rate, which is called a logistics model, so I should probably put that here. This is the logistic model here. This is something that you need to actually memorize, okay? So just like memorizing that if you have the rate of change proportional to y is an exponential model, you also need to memorize this logistic model. All right, so again, it's a differential equation, so you have dp dt, which is the rate of change of a population, equals k, and here's where it's a little confusing because we have lowercase k and uppercase k. Lowercase k is just a regular old constant, p is the population, and then here's the big one, the capital K is what's called the carrying capacity. All right, so you have to memorize this formula, so make sure it's in this format of 1 minus p over k, and we'll look at that later. All right, so just a couple of things that you need to know about this. So if p is relatively small compared to k, so that is if you have, so when you're looking at the formula and you have 1 minus p over k, and p is smaller than k, and like a lot smaller than k, then what this is approaching would be 0, right? So then you would just have 1 inside that parentheses, so therefore the population is approaching kp. And if you look at that closely, what that looks like is exactly what we started with all the way up here. Okay, we have the rate of change equal proportional to the population. So what that means is if the population at the beginning is very, very small compared to the carrying capacity, that is, if I start off with 2 rabbits in an island that can hold 10,000 rabbits, then they are going to increase exponentially at the beginning. So that means it's going to follow an exponential model in the beginning. Okay, so a relatively small beginning population with a larger carrying capacity, it is going to look like it grows exponentially. But as P approaches the carrying capacity, so that means as P gets closer and closer to K, then this is approaching 1. And so then this whole thing is equaling 0. So the rate of change is approaching a slope of 0. That means we are leveling off as we approach the carrying capacity. So it's no longer looking exponential, but that rate of growth is slowing down. Okay? So those are, again, are something to memorize. All right, and something else just kind of going along with that, if P is less than K, then the rate of change is greater than 0, and the population is increasing. So if my initial population is smaller than the carrying capacity, then my population should increase. And then if the population is greater than the carrying capacity, then my population is going to decrease. And of course, yet again, this is some kind of information and theory and stuff that you need to definitely memorize. All right, so let's see how this looks as an example. So we have a logistics equation. They give us the two K values. They give us lowercase k, uppercase K, and they want us to write the logistic differential equation. So if you need to refer back to the other sheet, you would get dp dt equals K, lowercase k, times my population, times 1 minus P over the carrying capacity of 1,000. All right? Now, we have a slope field. So we can't, it's very difficult to get an actual equation for P, and that's something else that we could look at, but we're not going to, because it just gets really, really complicated if I want to solve for P. So we have a slope field to kind of show us a model of different populations. And as you can see, at 1,000, we have the carrying capacity, and that's an asymptote. Because if I'm below the population, we shouldn't exceed that carrying capacity. All right, so just like we've done before, we're going to have these different starting points, and we're going to draw the slope field, or the solution curve for the starting point on the slope field. So if my initial population is at 100, okay, we're going to start off pretty slow increase because we don't have that much population. But as we follow this, we see that our population is increasing. And actually, if we stop right there, it looks exponential. But around in here now, as we're getting closer and closer to 1,000, this starts to level off and approaches that horizontal asymptote of 1,000. Okay? So then if we do starting at 400, now 400, we're already kind of a pretty large population compared to 100, so we're already kind of a little bit steeper, so we're going to level off a little bit sooner. All right, and then for the last one, 1,300, which is above 1,000, where you see we have negative slopes that are above 1,000, so we're going to have to decrease to reach that carrying capacity. All right, so here, I know this is a question, but also these right here are actually concept questions that you will have to memorize as well. So if I were to ask you where are the slopes the smallest, that's pretty self-explanatory. The slopes are going to be the smallest when the slopes are approaching 0. So that is close to the carrying capacity, which in this problem would be as P approaches 1,000. Okay. Then all solutions move towards, again, the carrying capacity. Where are the slopes the greatest? Now here are some really big questions. Where are the slopes the greatest? So if you look here, let's look at the green graph with a starting population of 100. I said that at the very beginning we followed an exponential curve, and then right about here we started to kind of change our course, all right, and our slopes started to decrease. So right in here, our slopes, where the population is increasing, but also the rate at which the population is increasing. Slopes are increasing here. But then right around in here, after that, my slopes are, population still increasing, but at a slower rate. So the slopes are decreasing. So what does that mean? Again, this point right here, hopefully you've already thought about it, it is a point of inflection. Okay, so that's something that you need to know. So a point of inflection is going to be where the slope has a maximum, and so that is where the slopes are the growing the fastest. So if you look over here, where does that occur? It looks like it's about 500, which actually, and this is true for all logistics, is half of the carrying capacity. And so that is something that you have to memorize. The slopes are going to be, the population is going to be growing the fastest at half the carrying capacity. So that's where you're going to have a point of inflection. So this is half of carrying capacity, which in this problem would be 500, which is the same as your next question, solution curves that start below 1,000. And actually, that should really be below 500, have inflection points when P is approximately 500. Because if you start above 500, you already passed that inflection point, so there's really no inflection points past 500. So really, that should be 500 on the Okay, and that in a nutshell is logistic equations. It's really simple. So the main things you just need to memorize is the formula for the logistics model, and also all these like theory questions, including the half the carrying capacity.